good morning, everybody. Or I guess after at 12:01 it became afternoon, right? Unless you happen to be in the state of Alabama, which it's still morning, I guess. It's still 11:01. So I think Mike wanted me to do some talks on motor protection. And so the first one of these, I thought we'd talk about the motor thermal model. Okay. So hopefully we can get through most of the motor thermal model in the next hour. There will be a few polls, and we'll do some polls during the course of this presentation. And if you've been on some of John and Mike's calls before, you're used to these polls by now. And so you know how that sort of goes. If not, Mike will explain it to you. And probably what we'll do is at the end, we'll take a poll around what you'd like to see next, right? So there's some options we have. So first thing, let's get cranked off. And before we start, let's start with the poll. So Mike, you want to go ahead and pop up my first poll question? Okay, guys, there's the first poll question.
You know, Terry,
so what do you got?
You had to start off like that, didn't you?
Yeah, I did. I am fascinated to see what you guys think about this particular poll. This is the main reason that I ask Mike to be able to do the polls. And I don't know that he always shares the results of the polls, but I certainly want the results on this, right? Okay, Mike, I think they've had enough time probably to look at this poll and deduce the correct answer, right? So if you want to proceed on, I'm going to proceed on. Is that cool?
Okay, I'm going to share the poll results real quick.
Okay, yeah. What are the poll results?
Okay, John apparently strained his voice.
Oh, see, I always thought it was a radioactive spider. Few people know that there is a working nuclear reactor underneath the Georgia Tech campus, and that's where John got his radioactive spider bite. Okay, so I hope I'm sharing my screen again around motor protection fundamentals. Before we get cranked off, let's talk about what can go wrong with a motor, right? And there's a lot of things that can go wrong with the motor. So let's look at some of the motor failure mechanisms. So there's several electrical failure modes. So, one of the things that we could have is we could have a stator inner turn failure. So the stator insulation could fail, and we could have a turn-to-turn fault inside of the motor. We could have a stator ground fault. So again, this is the stator insulation failing, and we've got a phase to ground fault like this stator ground fault that we see right here. See all that burnt stuff right there? That's the stator ground fault. Stator inner turn fault, right? So we could have faults. Again, this is stator insulation failure, and we could have these faults between the turns. We could have unbalanced current. Now, this unbalanced current may be caused by these turn-to-turn faults, stator ground fault, or it could be caused by power system conditions. That unbalanced current can be a problem for us and can cause the motor to fail. If we lost the load or the process, undercurrent or under power, that's not really a failure of the motor itself, but that's a failure of the process, and we might want to trip for that. We could also have, especially on synchronous motors, we could have an unusual power factor. We could also have an over or under frequency. Now, these sort of failures, we would protect with what I would classify as electrical protection. Now, we're not going to really talk about a lot of these sort of failures today because we're going to use our time to talk about the motor thermal model. Now, inside of the motor thermal model, that's where we can have some of these sort of failures of the stator insulation. Now, there are a lot of things that can cause problems with the motor thermal and cause a motor thermal failure. So we can have an increase in load. Let's jump through this this build real quick. So we can have an increase in load. This is going to cause extra load to be on the motor. Extra load means extra heat, and we can start to fail the stator insulation because of that. So that is one of the main things. But then there's a lot of other things, like we could have locked rotor conditions. We could have some extreme starting conditions or start and then restart. We could have an unusually high ambient, or we could lose the cooling. We lost the cooling, we might have problems. We would have to use RTD or RTD biasing to protect for that. You know, just as I mentioned unbalanced conditions, those unbalanced conditions will also cause rotor heating, or they'll cause heating. And because of that heating, we need to be able to trip the thermal model. Now, what I'm going to talk about today, all of these things that are feeding into the motor thermal failure, that's what I'm talking about today, protecting the motor with a motor thermal model. And this is mainly around protecting the stator insulation from overheating. So there are a lot of things that can cause this, as I just mentioned. So this can be process caused, is if I have a excessive load, if I've got a high ambient condition, or I have blocked ventilation. These can all cause extra motor heating, which can cause me problems. If I've got this unbalanced condition from the power supply, that's another one. Also, if I have, you know, along the same line, if I've got phasor ground faults elsewhere out in the power system, they're going to cause some unbalanced conditions, and they're going to cause some extra motor heat. So I'll need to take care of those. But on top of that, there are a lot of things that we need to take into account in this motor thermal model that are more or less sort of abnormal operating conditions. So these are under voltages or over voltages, under frequency, a voltage or current imbalance. If we lose the load, we jam the motor, jogging motor, or what I would also add there that I don't show on the screen is unusual starting conditions. So we're trying to restart the motor too soon.
Is there a lag?
No, the lag's not
Voice.
Okay,
too bad.
so I think I need to slow down a little bit between my slides because there's a bit of a lag between the video and the audio. So I'll do that. There's also several mechanical failure modes that I could have. I could have a broken rotor bar, could have a mechanical jam. So in other words, if I'm my motor gets jammed and it stops, that's going to cause a mechanical jam. I could have a bearing failure. This is another mechanical problem. If I have I could have an overspeed. So if I have a belt-driven system, and if my belt happens to break, I'm going to have an overspeed. And this is typically a process type problem rather than a true motor problem. I could also have loose foundations and misalignments. Also, I could have an eccentricity in the shaft. Again, we're going to talk about the motor thermal protection today. So we're not going to spend a lot of time on this, but a lot of these things that I show here, these are around mechanical items that I could protect with, or I could detect an alarm on with motor signature analysis. Now we'll do a poll later about where you want to go next. And in that poll, this is what I would talk about around when you see motor electrical signature analysis. Okay, I think that this is slide number 7. So before we hit into the motor thermal model, let's do our second poll, which the question in this poll. So Michael, if you want to share that poll. So the poll is, why do we need motor thermal protection, right? Do we need it for A, to prevent overloads from becoming electrical faults? B, to extend the life of the stator insulation? Or C, because the NEC says so? So interested in your poll answers here. We'll give you a second to respond. Oh, and I've got a there we go, John. I think I just turned off my webcam because it was eating up way too much bandwidth. I forgot me to do that earlier, but I've just did it now. Okay, Michael, they've had enough time, so let's see the results of the poll. Okay, what were the results, Michael? I'm having a hard time. I don't know how to see them.
You should be seeing them now. I got
Open up your polls.
42% to prevent overloads from becoming electrical faults, and 54% voted for to save or extend the life of stator insulation. We had 4% vote because the NEC says so.
Okay. Well, those are those are all good answers. And in fact, if we look at the real reason we do this, right? So let's come back to my presentation. The real reason we do that, it's a combination of all three of those things. So this is an instance, one of the rare instances, where almost anything that you would have said as an answer to that poll could have been the correct answer, right? Usually it goes the other way, where almost anything that you say is the wrong thing to say. But in this case, it's hard to go wrong. So the real reason that we use motor thermal protection is because it extends the life of the stator, right? The stator insulation specifically. Now, as we age that stator insulation, the failure mechanism is it eventually fails and causes a electrical fault. So this might be a phased an inner turn fault between turns, or a phase to ground fault. But those two things are connected, and that's why we protect. And so to put this into perspective, I really like this graphic that I show on the screen right now. And if we look at the F-class insulation, so let's take a look at the F-class insulation here to help us understand it. So F-class insulation is rated for about 155 degrees, right? So imagine that's a straight line right down. That's hitting at 155 degrees. So as long as we keep that stator insulation at a temperature less than 155 degrees, we have 100% of that stator's insulation life left. Now that doesn't mean we've got 100% of it. So in other words, if the stator insulation, if we expect that to last for 40 years and we have run the motor for 20 years, then we've got 20 years left. We still don't have 40 years, right? Or the expected life of 20 years. But let's look at what happens if we exceed that 155 degrees by a mere 10 degrees. So instead of we reach 165 degrees on that motor insulation, we've reduced that time down to 50% of its original life. So using the same scenario is if we have a motor, we expect that motor stator insulation to last for 40 years, and we are at the 20-year mark, so we should have 20 years left, but we exceed the stator insulation rating of 155 degrees and go up to 165 degrees for a short amount of time. Instead of having 20 years left, we've got 10 years left, right? And so if we operate it for another year and we exceed it again, instead of having 9 years left, we exceed it by 10 years, we got 4.5. So you can see how exceeding the insulation class of the motor stator insulation really starts to deteriorate the insulation and break down that insulation. So once that insulation breaks down, we're going to have a fault, and we're going to have an electrical fault. So what we're doing two things. We're extending the life of the motor, and we're also keeping the stator insulation from breaking down and causing a true electrical fault. Okay, so at the heart of the motor thermal model is this picture that I show right here. So what the protective relay does is it builds a thermal model in the relay. Now, it builds that thermal model based on settings and measured quantities, right? So measured quantity is the current that is flowing into the motor. also the unbalanced current, things of that nature. It might also bias that thermal model based on measured temperature. But basically what the relay then does is it builds a thermal capacity used based on that thermal model. So if we look at this beaker-like thing over here on the right, so this bucket, let me find my pen. So here's my beaker-like thing. It fills that beaker based on these measured quantities and settings. Now, we can see how full that beaker-like thing is by going to actual values on a protective relay. We go to actual values and metering and the motor, we can see thermal capacity used of the motor. Now what the relay does is and it's expressed as a percentage. So when it hits 100%, that beaker-like thing is full and the relay trips the motor offline. And so that's sort of how this thermal capacity used works. Now it builds that thermal capacity used on a lot of settings: the overload pickup setting, the overload curve, the running and stopped cooling constants are used. So the running and stopped cooling time constants are used in modeling how fast the motor cools. It also uses the hot to cold safe stall ratio, and that's used to determine what level that red lava-like fluid that's flowing into this beaker-like thing falls to in the steady state. And then also it can use RTDs and unbalanced biasing, as well as the motor state machine. I'll talk about the motor state machine in the next slide, but the key thing that we should take into account here is that when we start the motor, the relay will calculate a lot of thermal capacity used because we're starting the motor, we got locked rotor conditions, we got to get this motor up to speed, we generate a lot of heat. So during a motor start, that thermal capacity used, it may fall up here to 80% or so, right? So it may fall up here to 80%. After the motor gets to running for a while, at or below load amps around, less than pickup of the thermal model, it will fall to some state, right? So that bracket there is what it's falling at. So it'll fall to some state in the steady state. Now the rate at which it falls, that rate at which it falls is determined by the running cooling time constant. So how fast it falls to that steady state value is determined by the running cooling time constant. The level to which it falls to is determined by the hot to cold safe stall ratio. So it's actually 1 minus the hot to cold safe stall ratio is the level that it falls to. So if our hot to cold safe stall ratio, which is a setting in the relay, if it's 80%, 1 minus 0.8 is 20%. So this particular motor would fall to 20% thermal capacity used in the steady state. So another thing that this thermal model is used for is to inhibit a start. So for example, if I started this motor and it takes 80% thermal capacity used to start the motor. Now, the relay can learn that it uses 80% thermal capacity used to start the motor, and that can be its learned value of starting thermal capacity used. So if I start the motor, it generates 80% thermal capacity used, and I run it for some time. The thermal capacity used falls down to, I don't know, 60% here. It falls down to 60% here, and I stop the motor, and then I want to restart it. I can't immediately restart the motor because I'm at 60% thermal capacity used, and the relay knows that it takes 80% thermal capacity used to start the motor. If I tried to stack in that 80% thermal capacity used into this 60% thermal capacity used right now, I'd be at 120%. I'd be overfilling my beaker-like bucket here, and I would trip. So the relay will start inhibit for that. Now, I already mentioned that the rate at which that red lava-like fluid drops is in the running state is based on the running cooling time constant. When I stop the motor, the rate at which it falls is based on the stopped cooling time constant. You know, another great example of this is if I start the motor, I generate 80% thermal capacity used, and I run it for some time, and I drop back down to my 60% right here. So I'm at 60%, and then I overload it, and I start to overload it, I will start to generate that red lava-like fluid. And when it reaches 100%, I'm going to trip, right? So the key thing for us through the remainder of this time to sort of understand is how the relay builds this thermal model and how it models that red lava-like fluid flowing into my beaker-like thing. So in the next few slides, we're going to talk about how we build that motor thermal model based on settings. But before we do that, Michael, we have another poll. Would you care to share that poll? Hey, Michael, can you share the poll?
He did.
Sir, just heard it.
Oh, okay. I'm not seeing it. I don't know. Yeah.
If you look at the menu, you should be able to drop down the poll, and then you can see the results.
Is the menu on my control panel?
Yeah. Right below dashboard should say polls.
I may have to make you an organizer instead of a presenter.
Yeah, I don't think I can see that. Okay, what's the results though?
Okay. We have a winner.
Okay.
A weird breaker-like thing.
Yeah, beaker-like thing. Yeah. Okay.
Oh,
I will continue to call that a weird beaker-like thing in all of my presentations henceforth. Okay, guys, let's jump on into the rest of the presentation. Okay, so there are some important things that the relay needs to determine, and one of the first things is the motor state machine. And what the motor state machine basically is it helps the relay to determine what the state of the motor is. So, and it all hinges around what is the stopped state. So stopped is when either the current is less than a threshold value. That's usually about 10% of nominal current. So if current is very low, it says the motor stopped, or it's around zero, I guess would be a better way to say that. The other way that the relay can determine that the motor is stopped is by either the contactor or breaker status. So this is a 52A or a 52B contact that's wired to the relay. Okay, now the next state is the starting state. Now, what the relay declares a motor to be starting when the previous state was stopped and we are above full load amps, right? The next one is the running state, and that's when the previous state was starting or overload and current drops below pickup of the motor thermal model. And then the overload state is when the previous state was running and we are above pickup of the motor thermal model and we're starting to accumulate thermal capacity used and overload. Now, the reason this is really important is one of the things that I've seen a lot of people get incorrectly is they would have wired a 52B finger to the relay instead of a 52A. Now, most relays give you the choice. They say, hey, as a matter of setting, have you wired a 52A or a 52B to this relay? If you wire a 52B and tell the relay that is a 52A, then the relay thinks the contactor is closed. So even though the contactor is open, the motor thinks, or the relay thinks the motor is running, because it never saw the current drop, or it saw the current drop below the pickup level, but it never saw the contactor open to go to the stopped state. So that can be a problem, because if you then try to start the motor and it sees that the previous state was running instead of stopped, because you've got a 52B wired and telling it's a 52A, it will immediately go into overload and you may trip the motor. Another problem is that there are certain elements that are blocked by this state machine. So for example, a acceleration timer is only active when you are starting the motor. Well, if it never sees it's in the starting state because it never saw that the stop state happened, it's going to trip. So key takeaway there is this state machine. It's important. The most important thing is that if you're wiring a auxiliary contact from a contactor or a breaker, that it is set for what the contactor actually is. There's also some states for synchronous motors. So in a synchronous motor state, there's a synchronous motor stabilizing. So that's basically the previous state was running, field is applied, and we're waiting for the load application delay to expire. Synchronizing motor running is the previous state was stabilizing, and now load is on the motor and current must be less than overload. And then there's a resync state in a synchronous motor when the previous state was running, but we've had a power protection trip, and that's tripped the field. Okay, so let's talk about how we set the motor thermal model. Now, the way that we set the motor thermal model will dictate how fast and how correctly we feel that beaker-like thing, right? And how fast that we cool and the lava-like fluid decays or increases. So it's very important, not only for protection, that the motor thermal model be set correctly, but also so that we can get the most out of our motor and not trip erroneously. So one of the key things that we'll need is some information about the motor. Now, sometimes we have great, wonderful data sheets, right? And if we have a great, wonderful data sheet, it might say use curve 8. And if it says use curve 8, we know how to set that. We use curve 8. Sometimes we'll have curves like this motor thermal limit curves, and this comes from the motor manufacturer. Now, in this motor thermal limit curve, we get a lot of good information, and we'll talk about that in a few moments. And then sometimes we have a motor that we don't have a lot of good information on. The data sheet, motor might be older than us, and they don't have the data sheets from back then, and all we've really got is the nameplate. And so we really need to be able to set the motor for any of those conditions. But either way, one of the things that we really need to do is be able to understand this motor thermal limits. So if we look at this, the graph that's on the screen there, what we see along the bottom axis down here is the stator current in rated current, right? And this is the time along this axis, right? So F and E here, F is 100% acceleration curve. So what that means is this is probably about 6.5 sitting right here. So that's where locked rotor amps are. So that's the current we're going to draw when we got 100% voltage and we start the motor. Starting time is where this dude goes flat right here, right? So that's the time here. That's what the F curve is. Now the E curve is like it, except the E curve is for 80% voltage. And then C and D are a locked rotor damage curve, hot and cold. C is the cold, D is the hot. A and B are the cold running overload and the hot running overload, right? And so those are those A and B, those are where we would start to damage the stator for running in an overload condition. C and D is where we would damage the rotor in an overload condition. Okay. Now, one of the first things we really need to set is the pickup of the motor thermal model. Now, when we set the pickup of the motor thermal model, we don't want to set that at 1 per unit or full load amps of the motor. The reason we don't want to do that is because if we do that, we end up not being able to fully load the motor. So we set the pickup with some margin. Typically, that's around 10%. In that margin, we also want to accommodate the fact that we probably have a service factor on the motor. Now, the service factor will also let us do some overload on the motor. So we typically take that service factor and multiply by that 10% margin. So for a service factor of 1.0, we set our motor thermal overload pickup at 1.1. Now, this margin accounts for a lot of things. It accounts for the fact that we might have some CT errors, some other errors, and it lets us fully load the motor. Typically, you can see service factors that go fairly high, or not necessarily fairly high, but we can see that go up to about 15%. And if it goes up to 15%, the maximum you can typically set the pickup of the motor thermal model is 125%. Now, the reason that that's limited to 125% is because the leads to the motor will need to be protected by the motor thermal model. We cannot protect the leads to the motor by a time overcurrent, because if we did, we'd never be able to start the motor, because we draw 6.5 times full load amps at locked rotor conditions when we start the motor. Well, that's 6.5 times. If we tried to do this with an instantaneous overcurrent, protect the leads, we would trip. So what we do is we roll the leads into the motor thermal model typically. The NEC requires us to oversize the leads by 25%. And so by fixing that at 25% for the overload pickup, we're able to protect the leads as well. Okay. So once we set pickup, we're going to start to build the thermal model. Now, there are a lot of things that beyond just the settings inside the relay that we need to account for. So I've already talked about how we build or how we accumulate thermal capacity used, and it is basically represented by a percentage, but there are things that go into that. So we need to model the motor losses, those generate as heat. We need to model unbalanced current because those will generate heat. And we may need to model the ambient temperature or loss of cooling, because if all we're modeling comes from this CT that's sitting right here, we don't really know if the fans are blocked or the fans aren't there, or if we have an unusually high ambient. So we need to account for that. So the first piece for this is to select a overload curve. Now, if we have this information here, this is the midpoint, right? So if we have these motor thermal limit curves, then what we'll want to do is we'll want to choose a curve that is just below the cold limit curve, right? Now, that's what we do if we have this information. Even better than this is if the motor manufacturer's data sheet says use curve 8 or use curve 6, we just use curve 8 or curve 6. We follow their recommendations. Now, in a worst case scenario, we don't have a sheet like this. This is the scenario where I said all we've got is a nameplate. So if we don't have anything but the nameplate, one of the things that we can do is we can start the motor, hopefully. If we start the motor, we know this point here because that's locked rotor amps. That's the amps that it draws during locked rotor conditions. We also know how long it takes the motor to start. The relay can actually learn and give you that. And if we know that, we know this point where those two intersect. And if we know where those 2 points intersect, we can lay a curve just above that. Now, since we don't have this sheet, we don't know how far below the limit curves we are. We don't even know if we're below them. But what we do know is we're going to be able to start the motor without nuisance tripping if we do this. We've got to make do with what we've got, right? If we have to assume that we are below those thermal limit curves. Now, what I mentioned earlier is if we do have these motor thermal limit curves, we want to set it just below the cold curve. Sometimes we don't get both curves. Sometimes we only get a curve. If we get a curve, we don't really know, but we're going to set it below that curve, right? So if we're only provided a hot curve, we should just go below that hot curve because we don't know where the cold curve is. Now, a question that often comes up is, why can you set this just below the cold curve? Why are they giving me a hot curve? The reason I can set this just below the cold curve is because we will use the start inhibit to protect ourselves from starting on a hot curve, right? So the start inhibit is this mechanism that I mentioned earlier where we're going to use the motor thermal capacity used and the learned starting current to inhibit a start until we have enough thermal capacity used to actually start. Okay? So the next setting that will become important is the hot to cold safe stall ratio. Now, the hot to cold safe stall ratio is just as the name implies. It's the ratio of the hot to cold safe stall time. The reason that this setting will be important is because the relay will calculate a thermal capacity used that the motor runs at in the steady state. So what I mean by the steady state is what it falls to when it's running at or below pickup of the overload curve. So this is typically of a value of around 80%. The value that it falls to is 1 minus that. So it'll fall to about 20%. So how do you get this hot to cold safe stall ratio? So if we have these, so if we have a data sheet and it says the locked rotor times, and it gives us those locked rotor times in seconds, we can merely take that ratio. That's our setting. If we don't have that, and we do have this thermal capacity curves, we know that this is the locked rotor current right here, right? And that this point right here is the hot safe stall time, and that's the cold safe stall time. We could read across here and get those 2 times, and at this point, that's 8 seconds, or 6 seconds and 8 seconds. We could take that ratio, and that ratio would get us our hot to cold safe stall time. If no times are provided, then what the manual represent, or what the manual in most of our relays suggest, is that we set it to 1, right? And that's a worst case scenario. Again, if I've got that data in the data sheet, I can just take that ratio and get it. Now, once I've set those things, most of my overload curve is built. Now, 2 very important settings that I still need to enter, and we'll talk about those here in a few minutes. Oh, and I jumped through a slide. Or I jumped through a poll. So before we proceed, let's do the next poll that I should have done at slide 15. So Mike, would you care to share that poll?
Okay, Terry, it's open, and the question is, how often do you have good data from the motor manufacturer to set the motor thermal model?
Okay, Michael, what are they saying?
Let's give it another 10 seconds. That's an almost perfect C curve. Here, I'll share it with you.
So I can't see that screen.
So we have 48% voted sometimes,
Ah,
and then
yeah.
4% voted never and always. And
Okay.
so we had, like I said, a perfect, C curve.
Yep. You just got to work. You just got to figure out who those guys are that always have good data, right? And make your life easy.
Yeah, yeah.
Yeah. Okay. So let's talk about some other curve settings. So there is the ability to build some custom overload curves, right? And I'm going to have to speed up or we're going to go way over. So we can build some voltage dependent curves. And basically, if we have a really high inertia load, like an ID fan, it takes a long time to start those motors. So, this particular curve here, we're looking at 100% voltage, it takes it like 20 seconds to get up to speed. And sometimes that starting curve can infringe on the thermal limit curves of the motor. And that's especially true if we happen to collapse our voltage to 80% during a start, right? Then we can really be in trouble. Now, there's a couple ways that we can do that. One of the things that we can do is to build a custom curve like I show here. And in a custom curve, you actually have to add the values and build sort of a custom curve. So you pick up and time to trip, and that's how you build a custom curve. And doing that, you can notch out this section that I show here. That's one way to do this. The other way to do this is to build a voltage dependent curve. And so with a voltage dependent curve, what we do, we have to have measured voltage. So we have to have VT inputs to the relay to do this. And we basically dynamically shift the protective curve based on measured voltage. Now there's a few settings that we need to do that. And so if we look at this, number 4, so 5 and 6 here, these are the starting curves. Number 4 here is our locked rotor thermal limit. And then 2 and 3 here are the acceleration curves from that locked rotor thermal limit up to the stator damage curve or the running overload thermal limit. And so what we really need is we really need these values shown here. So we really need where these intersections are. So we need the time at those intersections. And those are going to, if we use a voltage dependent curve, these are the settings that voltage dependent curve will need. And then based on those settings and measured voltage, the relay can dynamically shift the curve to provide you protection. So in this case, when my voltage collapses to 80%, it's going to shift that damage curve like this. If I'm at 100% voltage, it shifts it back. Another thing that we need to account for and take into account always is the unbalanced current. So unbalanced current creates rotor currents that are rotating in the opposite direction. And they also, it's at twice system frequency, which causes a lot of skin effect heating. So this will cause rotor heating. Now this can be caused from any number of things, but they're all related to a unbalanced voltage, right? This is unbalanced current, but they're all related to unbalanced voltage, which might be from a blown fuse, which has caused us an open phase upstream. Loose connections, so we've got one more voltage drop across a connection of a particular phase than the others. We have stator turn-to-turn faults. We can have this. If we've got a unbalance from the power system, from our utility supply, or we've got a voltage distortion caused by faults, they can all cause this. So the way that the motor thermal model takes into account this extra rotor heating is by applying an equivalent current to the motor thermal model. And that equivalent current will use not only, I've lost my pen again, there it is. Will not only use a measured current here, the real motor current, but it'll also use the ratio of negative sequence to positive sequence current here and a K factor. And basically what this K factor is the K factor is basically saying how much do you want to derate the motor for this motor thermal heating. Now, here's a example from NEMA for different K factors. Now, typically NEMA recommends a number 8. And so what you see here is this curve here where you have percent unbalance along this axis. And then based on that percent unbalance, how much you derate. Now, a NEMA curve of 8 is NEMA recommendations. There's what we typically see is that customers use one of these two, either a typical value of 175 divided by the square of the locked rotor current expressed as a percentage of full load amps, right? So in other words, that's not locked rotor current there. That is a number that in each of these is a number that's more like 6.5 here and here. So these two numbers, so a value of 230 is really kind of equivalent to a derating factor of 6, and the 175 that is typical is more like a derating factor of 5. So that's the 3 different strategies you could use. If you wanted to derate it by NEMA, you can choose K of 8. But typically we see either this lesser value of, a K factor around 5 or a K factor around 6 based on these quantities here. Okay, so everything that we talked about so far around the motor thermal model doesn't take into account the fact that I may have an unusual high ambient, or I may have leaves or dust or other debris blocking the intakes to the fans that are on the rotor shaft. So because of that, we can also build an equivalent motor thermal model based on measured temperature. Now to do that, there's 3 settings that we need. We need a minimum value, a center value, and a maximum value. Now the minimum value here is where we are when we have a thermal capacity used. So this is stator temperature here in degrees C in this case. And it's a degrees C, yeah. And then along this axis, we have thermal capacity used. Now, when we don't have any thermal capacity used, we're going to be at the design ambient. So this particular motor looks like it's got a design ambient of 40 degrees C, so that's our minimum value. And in this alternate thermal model, if we're at 40 degrees C, we've got 0% thermal capacity used. Our maximum value is the next one. So when we're at the stator rated temperature, we are at our maximum value of temperature, and we should trip. We should be at 100% thermal capacity used. So our maximum value is going to be the insulation rating. So it happens to be that it's 155 degrees C. So this is probably F-class insulation, like the 6th or 7th slide that I showed where I talked about how if we overloaded it, for any amount of time, we would shorten the life of it. The center temperature here is where we sort of expect to be at the steady state. Now, in this case, probably our hot to cold stall ratio is probably about 85. The reason I say that is because it looks like for this thermal model, in the steady state, or when we're at rated temperature, we are about 15% thermal capacity used. So that's the value that we fall to in the steady state. So how do we determine this RTD by center point? This is going to be the design ambient plus the rated temperature rise plus a 10°C hot spot allowance. So it looks like this particular one, it's probably got a 40°C design ambient. What is that, 125, you think, right there? So that'd be 125. So that's probably about 130°C. So it's probably got 130 minus 40 is 60, 50, yeah, 60°C, no, 70°C hot spot allowance, temperature rise plus the 10°C hot spot allowance gives us to the, looks like 125 or so. Okay, so the next thing that's really important, the last thing that I really want to talk about is the running cooling time constant, running and stopped cooling time constant. So what these two settings do is they model how fast your cooling time decays. Now this is an E function, and if you're like me here lately and you look on social media, I always used to get irritated by the people that were always like to correct people's grammar, right? And now here on social media, I always get irritated by all these people that I've become one of those people, but not about grammar, but about mathematics, right? In this weird time, especially during the start of the quarantine, a lot of people posted mathematical things that were just wrong. But this E function is if you look at how this is decaying, so this is the running cooling time. So this is time in minutes. This is thermal capacity used here. So it looks like we started the motor, we generated about 85% thermal capacity used during the start, and then it cooled down to about 20% thermal capacity. So probably have a hot to cold safe stall ratio of 80%, so that's 20. But it cooled down over, it reached that at about 60 minutes, right? So if you look at how it's cooling, this is an E function. So what I mean by an E function, this is the number E raised to minus a time divided by a time constant. That time constant is this cooling time constant that we asked for in settings. Now, the actual cooling time will be 5 times that cooling time constant. So 5 times 15 should be about 75 minutes, which would be about right here. And yep, that is the time, the actual cooling time that it took to fall to the steady state. Likewise, here's a stopped motor over here. Again, time in minutes here, thermal capacity here used here. This particular motor looks like they reached 100% thermal capacity used and they tripped. After they tripped, the motor had to cool to some value. It takes 5 times the cooling time constant, which cooling time constant stopped is 30 minutes. So that should be 5 times 30, that should be 150 minutes to reach a steady state, which is what it takes. Now there's a couple things to take in here. The first thing to take in is that the cooling time constant running is smaller than the cooling time constant stopped. Now the reason for that is it will cool faster running than it will stopped. The reason it will cool faster running is because there are fans mounted on the shaft, and those fans help to cool it. Now it'll cool faster, but it'll cooler to a higher value, right? 20% versus 0% here. The other thing that we should take in is that this is cooling time constant. So as I mentioned, that E function, E raised to a, 1 minus T time divided by cooling time that cooling time constant is the setting. Sometimes on motor manufacturer data sheets, you will find a cooling time rather than cooling time constant. That cooling time is 5 times the cooling time constant. So that's how I got this 150 right here. I took 5 times the cooling time constant of 30 minutes to figure out how long it would take to cool the motor. Now, the reason I want to highlight this is because what happens if I find a value for cooling time of 150 minutes for this particular motor, and so I find 150 minutes and I enter that for cooling time constant incorrectly. If I enter that for cooling time constant and it's really the cooling time, instead of being 30 minutes here, this is 150 minutes. So if this is set correctly at 30 minutes and I trip, looks like I generate, I don't know, 85% thermal capacity used during a start. That means I need to have room for 85%. So I need to drop down to about 15% thermal capacity used before I can start. So that's around, let's call that 60 minutes because I probably didn't draw that exactly right. So if I actually trip this motor to be able to fit that that learned thermal capacity used during the start in there, I'd have to wait 60 minutes before I can restart it. That's if it's set correctly. If I inset this incorrectly and enter cooling time versus cooling time constant, I'm going to have to wait 5 times longer. So instead of being able to start this motor after an hour, I'm going to have to wait 5 hours. So it's very important that you enter that as cooling time constant rather than cooling time. Again, if you cannot find that information on a data sheet or something else, the only thing that you can do is live with the default values in the relay, which are 15 minutes and 30 minutes, which these are the actual default values. So I think I've described everything there. So with that said, I skipped a poll, Michael, I'm sorry, but I think you had one other poll. So let's do that poll and we can address any questions that come in the chat.
I apologize, I was muted. The question is, how often do you use RTD biasing? The choices are never, sometimes, always, or what in God's name is RTD biasing? I'm gonna leave that up there for 10 more seconds.
I figured out how to be able to see what the audience is seeing. This is all.
Okay, here are the poll results. Never, 35% of you answered never. 48% of you answered sometimes. And 17% answered what in God's name is RTD bias. Back to you, Terry.
Oh, did you have another poll about where we go next?
I do. Would you like me to put that one up?
Yeah, let's do that.
Here we go. We're trying to get some input from the audience on what topic would you like to be part 2 of motor protection. Should we focus on the electrical signature analysis, which is an innovative way to preemptively detect such things as a broken rotor bar or a loose footing or shaft, a bent shaft, or a other mechanical issues that can now be identified by the harmonic signature of the motor. We could focus on electrical protection, where Terry perhaps puts some of these settings in a actual motor protection relay. Or we could focus on some case studies of a customer who called.
Electrical protection was actually the next step beyond this. How we determine and detect that we actually have an electrical fault in the motor.
Okay.
And you can vote for more than one.
And you can vote for more than one. That is correct. And we can focus on some case studies where a customer could not get a motor started, and after calling AAA, leave that up for another 10 seconds. And we have a winner.
What's the winner?
Electrical protection.
Okay.
So what I would say we do is have part 2 be electrical protection, and then have a part 3, which is electrical signature analysis.
Okay. So we'll do that part 2 whenever you've already sent. I think you've already set that up, but we'll do that then. So Michael, would you care to remind people how they can ask questions in this format, and we can address any questions that come in?
So there's a question button on the right side of the screen, and please feel free to ask questions. This is a lot of material in 1 hour of time. So far, we have no questions.
We have no questions or no good questions? Because there's a difference.
Both.
Okay.
Okay. I have some questions, though, if you'll go back to the voltage.
The voltage dependent curve
slide
that I went through super fast because I was trying to finish it on time and be a pro and end right at the hour like John Levine expects, right? Is that what you want me to do? Let me
I
get
suppose.
there. Yeah. Okay.
You got to slide up your post tool.
Yeah. I'm sharing. If you want to go back to my screen.
All right, I'm going to go ahead and close the poll.
Yeah.
Right now I see a GE. I see the meatball.
Why is it not showing this slide that I went to? Is there that much? There we go. Okay, what do you want to see? What do you want to talk about?
So it's at 80% voltage. How does it get to 80% voltage? Is this a voltage drop that occurs because of the inrush current?
Yes, that's a good question. So, and the answer is yes, but it's more complex.
Oh, good, because I was worried it was a stupid question.
No. Yeah, you should worry because I'll point out stupid questions, right? I'll say that's a stupid question. Now,
Thank
you attendees, that feel free to ask your questions. I promise I won't say to you that that's a stupid question. I'm not to Michael. But basically, this particular motor especially is troublesome because this would, when I typically start talking about these voltage dependent curves, I think about these really long start motors that really have a high inertia associated with them. So an ID fan is the best example of these. These are hard to get started. So there are a lot of different strategies you can use. One of the strategies is a voltage dependent curve. Another strategy that you could use is any number of soft starting mechanisms or VFDs or things like that. But nonetheless, anytime you're starting a motor, you're drawing a lot of current. So when you start that motor, you're at locked rotor current, which is probably around 6.5 times, full load amps. So if this is a 1,000 amps full load, this is 6,500 amps. Now that 6,500 amps, as it's drawn through the entire power system, will create voltage drop along that entire power system. So by the time you get to your motor, you could have significant voltage drop. So that's why we talk about this 80% voltage drop. So depending on the backbone, the muscle of your power system, how strong your power system is, and how deep into your own plant you are, which those two are basically the same thing, will dictate how much voltage drop you have at the motor when you're trying to start it. So yes, it is a result of that large current that you're drawing to start the motor, but it's also a result of how strong your power system is. So if you've got a really strong power system, you're not going to drop much voltage, and you may be at 100% or close to it. If you've got a weaker power system, then you may drop significant voltage and be at this 80% voltage when you try to start that motor. Make sense?
So let me repeat back to you so I understand what.
Okay.
Is it a 1 or a 0? Is it basically a digital, like it's moving the curve at 80% voltage, or is it sort of an analog? Is it moving it along the line?
Oh, okay, yeah. So I answered the wrong question. That's not untypical. I think your real question was, how does it move it? Does it either move it from 100%, which would be right here, or excuse me, right there, or 80%? It is dynamic, right? So at 80% voltage, we would be here, right? But if we were somewhere between 80 and 100% voltage, what's halfway between 90? We're at 90% voltage, we'd expect to be about halfway between those two, and our protective curve would look, well, it'd be a straight line, but it'd be more like that. So yeah, it is exact. It's not digital, and it flips between 100% voltage or 80%. It actually moves that curve, shifts that curve linearly based on the actual measured voltage. So if measured voltage is 90%, it's going to put it where I just drew that curve, which is halfway between the 80 and the 100.
Perfect. Thank you. Here's an interesting question that I certainly don't know the answer to, but let's see if Terry does. How does the Multilin 269 Plus compare to an Eaton EMR 5000?
It's much superior. I don't know much about that particular Eaton relay, so it probably wouldn't be appropriate for me to compare those two.
Okay.
I told the person we'd contact him directly on that. Plus,
Sure.
Yeah, we'll get back to you on that one.
The 269 Plus is obsoleted, superseded by the 369 or the 869.
Yeah.
And all I can tell you is, regarding Eaton versus GE Multilin relays, GE Multilin, before it was owned by GE, invented and conceptualized and patented the motor thermal model.
We've definitely done it longer than anybody else. We're 3 generations ahead of everybody else. Any other questions? Terry, thank you very, very much. It's great.
No problem, John. And thanks
you
guys for giving me the opportunity.
Take care, everybody.